is that we want to assume that the speed of light in all inertial frames of reference, and we want to assume the principle of relativity. So these are the postulates of special relativity. And we also want to assume, though it's actually a consequence of the principle of relativity video, that there is no length contraction perpendicular to motion, length perpendicular to that direction. Okay, and if you watch the other video, this concept should be quite familiar to you. And we're going to say all these assumptions imply time dilation. Alright, so time dilation, or more specifically, that you'll think it takes longer than a second for a moving clock to register a second. And more specifically, so you'll think the time is off by a factor of 1 minus v squared over c squared. So c, we'll call the speed of light c. Okay, so this is the speed of light here, and it's a constant in every inertial frame of reference. It's the same value, and v will be the speed at which the clock is going relative to you. So the faster it's moving, the slower the clock will be. And so t0 is how many minutes the moving clock is registered, and tv is how many minutes you've registered on your clock, that correspond to the same number of minutes that they've measured. So if they've measured 3 minutes, then you've measured 3 minutes divided by this quantity, okay, which will be more than 3 minutes. And the way we show this, okay, so we want to make all the steps clear, is that time dilation for a special clock called the light ray clock. It's actually very simple. We'll see when we get to it. Okay, so we'll just show that time dilation happens for the light ray clock, and that'll depend on this perpendicular length contraction and the speed of light being constant. And then after that, so I guess time dilation is a statement for all clocks, so it being true for the light ray clock is not enough. And that's something I've been kind of unsatisfied with when I was trying to learn this. Everything was just shown for the light ray clock, and the argument ends. But you really have to extend the argument to all clocks. And this is where the principle of relativity comes in. So maybe we could say this is A, B, C. And we'll use A and C for the first one, and we use B primarily for the second one. Okay, so the first one. So what is a light ray clock? So a light ray clock is very simple. It measures time by reflecting a ray of light from one point to another. So light ray clock. So what it does, say it shoots a beam of light And so light emitter, light detector, and it basically keeps track of the time by how many how many times the light detector detects the light pulse coming back. So 1 unit of time is the light going up then back. Okay, so that's a really simple clock. You know, something takes a long time if there's a lot of return trips of light pulses, and it's a very short time if there's only a few return trips of light pulses. So that's what a light rate clock is. And you can see how each light pulse, the time it takes to do a return trip, depends on the distance between basically the emitter and detector from the mirror. So that distance is important, and also depends on the speed of the light. Okay. Now, so that's a stationary light rate clock. What happens if the light rate clock starts moving? So if the light rate clock starts moving, the light will look like it's going up at an angle. And then when it comes back, it's not going to be vertically below the mirror anymore. It's going to be as if it's zigzag diagonally. Okay. So if I'm watching this while not moving, it's not going to look like the light just goes up and down, because it's moving. The whole apparatus is moving sideways. It's going to look like it went diagonally up and then went diagonally down. Okay. So let's say it moved with a speed v. Now how does the measure of time seem to differ? Well, we said that the measure of time depended on the distance and the speed. So the distance is the same because there's no length contraction. So this is our assumption C. But the speed is different, at least in the vertical direction, because, well, the speed along the path of the light is going to be the same in all inertial frames of reference. So that's the assumption that the light travels at constant velocity c. But that doesn't mean it'll the vertical component will be the same as c. So the vertical component will now be different. And of course it's smaller because because it decomposes. So can you see how the speed of the light is still c, and it'll decompose into its vertical and horizontal components, where the horizontal component is essentially v. So the vertical component will be, the Pythagoras output. So it'll be the square root of c squared minus v squared. Okay. So the speed in the vertical direction, it used to be c, and now it's this. So it's changed by a factor of this over c. So the new speed is root c squared minus v squared over c times old speed, which upon simplification is equal to 1 minus v squared over c squared times old speed. And since time is distance over speed, then the new time we'll get will just be the old time divided by this, and that's exactly the time dilation formula. Okay. So this is the longer, I think, but easier part of this demonstration. So the next part we're going to do is the number 2. It'll be quite elegant, I think, compared to this, but you really have to switch your brain on to understand the logical intricacies of the next parts. Okay, so let's do the second part of this argument, where we want to show that the principle of relativity implies all clocks behave like the light ray clock. Okay. And and to do this, we'll need the principle of relativity in a slightly different format for convenience. So instead of saying physics is the same as in all frames of reference, initial frames of reference, we'll say that it's impossible for someone within an inertial frame of reference to tell whether he's moving at uniform velocity or stationary from entirely within the frame. So that's equivalent, because if he could tell, then he probably could have told that with a law of physics that differed. And if the laws of physics differed, doesn't differ, then how could he have done anything to tell the difference? So it's really an equivalent formulation, and so we'll use that. And so we'll still consider 2 observers. Okay, so let's say observer 1 is moving observer. Mo. Okay. And we have a stationary observer. Stan. Which basically, I guess, is like us. And so, first of all, and then there's a clock. So Mo is equipped with the light rate clock. Okay. And so let's start our argument. So the argument starts with let x be an arbitrary clock. So if we show it's true for x, then we'll show it's true for all clocks. So Mo is equipped with the light rate clock and x. Okay, and Stan is just equipped with some clock that he used, to time all these other things before. So both Mo and Stan, okay, agree how many ticks of the light rate clock and how many ticks of x have undergone, because these are just events that you can see, but they won't agree on how long it took for those ticks to happen. Okay, because Mo will think those ticks happened in real time, whereas Stan thinks those ticks happened slowly. Okay, so both agree on relative number of ticks of each clock. So this means if x undergoes 3 ticks and the light rate clock undergoes 4 ticks, Mo will think that and Stan will think that as well. So if the clock was going faster relatively, the light rate clock was going like 5 times faster than x, it'll still be going 5 times faster than x according to Stan. But what those times are exactly might not be agreed by Stan. Okay. Now, but what is the relative speed of the two clocks? Now, so this is where we use the principle of relativity, and we work entirely in Mo's frame of reference. Or we work entirely from the point of view of Mo. So, if Mo had been stationary, if Mo was stationary, he would think both clocks are the same. Okay, that doesn't mean they tick the same amount, but they measure time the same. We could even calibrate our clocks so that they tick at the same rate. So that 1 second corresponds to 1 light ray bounce, and it also corresponds to 1 x tick. And if that was the case, then Mo would think that they would both do 1 tick at the same time. Okay, because when it's stationary, the light ray clock is just another clock. It doesn't demonstrate any, time dilation. There is no time dilation when there's no motion. Okay, but this will help us because we said that according to the principle of relativity, Mo can't tell he's moving, so Mo will come to the same conclusion when he's moving. So Mo will still think this. In his moving frame. So if x goes one tick when Mo's not moving and the light ray clock goes one bounce, then he'll think that they'll both go one bounce in the moving frame by the principle of relativity. And since we know that both had agreed on how many ticks that they were going, then Stan, or us, the stationary observer, will now also think that the light ray clock and x agree. So therefore x undergoes the same time dilation as the light ray clock. And therefore, since x was arbitrary, all clocks undergo the same time dilation as a light ray clock, which was the time dilation given by the formula